Hello, so I'm going to be solving the Basel problem, a problem that took hundreds of years to solve, that was originally solved by Leonard Euler, go figure. The Basel problem is this. If you have the summation of from n to 1 to infinity of 1 over n squared, and what does that converge to? Or does it converge to anything? So you're adding up all these numbers to infinity, really. And it actually does converge to something very unique. Pi squared over 6, which may seem kind of weird because we're adding up all these rational numbers and somehow we're getting a pi, which, where did the circle come from? And it's irrational too. So this is a very unique problem here. And so Euler solved it using a different method. I'm going to solve it using the Fourier series. Fourier series didn't come out till a little bit after Euler came up with this. Fourier was later in the game. But the Fourier series is a work of beauty, so I just really want to go into the Fourier series real quick. So this is the Fourier series. If it looks intense, it kind of is. There's a whole class dedicated to this, which you'll learn in partial differential equations, or PDEs, if you are interested in the topic. He was able to solve the heat equation and then later the Schrodinger equation from his series, which were unsolved problems at the time. So this was a very, very useful problem here. Okay, so what it states is if you have a function that has to be continuous and has to be differentiable at least one time. Continuous, differentiable, and it can even be a piecewise function, as we later found out. So any function, you plug in your input, your domain, x here, is equal to a naught over 2. A naught is just some term here, which is already solved out for you here. I'm not going to go through how this was all derived. This would take a long time. Well, not a long time, but that's not part of this video. Really, we're just going to use this to get the Basel problem solution. Okay, plus the summation of an, which is already right here, written out for you, times cosine of n pi x over L. You may wonder what the heck is L, because when we're throwing in an x, we got an x, we know what n is, n's here, so we know what pi is, obviously. L, what is L? So when he originally derived or made his Fourier series, he based it on the diffusion of heat through a one-dimensional rod, which was the heat equation, really. So the rod was in length L, and so he went from negative L to L for his length. So really what L is, it's our domain, really. So we're going to change L around in this problem. We're not going to use L. We're going to have something else. And plus the summation of Bn, which we have down here, times sine of n pi x over L. So we use all of this. So this was derived from the heat equation, which seems like it would be a pretty easy equation, but it is a partial differential equation, so nothing easy with those. So the heat equation, really, I'm not going to go too in depth in this because this is not a video on Fourier series, but the heat equation states that the partial differential of heat, I'm going to use U as heat, in respect to time is equal to, and I'm being very generic with the heat equation, I know there's a lot more coefficients and external forces that come into play, but I'm being very generic here. So the partial of heat over in respect to time is equal to the second partial, that's not a 2, that's a, there we go, second partial of heat in respect to x, which if you have in physics class, it's a second derivative of x is kind of like acceleration, think about it. So this seems like a very simple problem to solve, but it was unsolvable until Fourier came around and solved it, and then later solved the Schrodinger's equation, which really, and then so much more came out of that. All of his PDEs. If you study quantum mechanics or the atomic theory or optics, you're going to see a lot of times this summation. And if you see all this and where this came from, now, this is really what it is because of the Fourier series. Okay, so what he did was he took this and used separation of variables. So he put all the t's on one side, all the x's on the other side, and set it equal to a constant. And then he was able to use ordinary differential equations to solve each one, and then use superposition to put them together. But that's a whole nother video for another time. That's just where the Fourier series was derived from. Okay, so we're going to solve the Basel problem using this Fourier series. So first let's state what our function is going to be. So our function I'm going to choose is going to be just x squared, which meets the criteria of being continuous and differentiable. And the interval is going to be such that x is in from negative pi to pi. So it's on the interval from negative pi to pi. So it's still differentiable. This whole thing is differentiable. So this is what our function is, and this is really our boundaries. Okay, so let's plug that into our Fourier series. So now instead of L, we're going to have a pi. So that's really the only difference that's going to go on right here, if you can see. We're not going to start working with this function yet until we start solving for these coefficients or these constants here. Okay, so let's see. Let's get into here. So let's write the Fourier series with this pi. Well, so I'm going to put this up here and copy this Fourier series down, but put pi here. So it's f of x is equal to a naught over 2 plus the summation of 1 to infinity of a n times cosine. Now notice here it's cosine of n pi x over L, but we're going to replace the L with pi. So it's just going to be pi over pi, so these pi's will just cancel out. So it's just going to be nx. So nx, and plus the summation from 1 to infinity, bn of sine. And notice sine will do the same thing. We'll plug in the pi, so this will just be nx. Okay, so now we have this guy going on here. Alright, so let's solve. What we really want to do is we want to solve for each one of these. We want to solve for a naught, a n, and bn. Right, so to do this, let's just use our formulas. So a naught over 2 is equal to this here. So I'm going to plug in let's just rewrite it down here. So a naught over 2 is equal to 1 over 2L. And if you work with these enough, you'll start memorizing these equations. Fx in respect to x. So the function in respect to x. So what is that really? So we're going to replace our L's with pi's. So 1 over 2 times pi. And our boundaries change from negative L to L to negative pi to pi. And our function, which we chose, was x squared dx. Alright, so now we can go ahead and solve this integral. And solving this integral is not too bad. First of all, notice that x squared is, it's a parabola, right? I mean, it looks like, that. So notice the right half is the exact same as the left half. So really we can just get rid of this whole left half and just multiply this right half by 2. So we can start this bottom boundary at 0 and multiply this whole function by 2. Or whole integral, I guess, by 2. So you can see 2 over 2 would cancel out. And the 1 upstairs. So let's just rewrite it again. So 1 over pi times the integral of 0 to pi this time, our new boundaries, of x squared in respect to x. Okay, so now this integral should be pretty simple to solve. This is basic Calc 1 here. So let's just write down this here, 1 over pi. So what's the integral of x squared? It's x cubed over 3. So this is times x cubed over 3. But we're on the boundaries from 0 to pi. Okay, we still got to plug our boundaries in. This is not an indefinite integral, it's a definite integral. So I'm going to plug my boundaries in. Notice the 0 one, if I plug 0 into here, it's just going to vanish. So the only one I have to work with is pi, which is nice. So let's plug these boundaries in. So it's just pi cubed over 3. And what's this equal to? So we just have, notice we have pi cubed over 3 over pi, which is just pi squared, over 3. There we go. And now we have our first term here, which is a2, or a naught, over 2 is equal to pi squared over 3. Okay, so I'm going to square this one just so keep it for later, because we're definitely going to do that. We're going to take all these and plug them back into this beast here. So let's next do our an. So I'm going to rewrite this just from memory. So an is equal to 1 over L times the integral from negative L to L of, this one's cosine n pi x over L times our function and divided by x. Okay, and what I'm going to do here is I'm going to just, like I did before, turn all these into pi's, all the L's into pi's. So this is 1 over pi times the integral from negative pi to pi of cosine. And notice yet again, our L is pi, so pi over pi goes away. It's just going to be nx times our function, which is x squared, and differential to x. Okay, so this is a little more tougher of a integral. This is a calculus 2 integral, I believe. First, let's make it real easy, much easier. Notice that cosine, so first of all, x squared is, a parabola, so we can do the same trick again. And cosine is also the same reflectiveness. And so we can do the same thing. So we can change this to 0, get rid of this whole half, and just multiply this part by 2. So put this 2. Makes things easier to integrate. Okay, so let's integrate this integral. Alright, so it's 2 over pi times the integral of 0 pi cosine at x. I guess I just copied it, really didn't do much there, of dx. So which makes this a difficult integral is we have to use integration by parts, if you learn that in Calc 2. But luckily there's a very nice method. If you have a variable that, if you have one part that will differentiate itself all the way to 0, you can use the tabular method, which is a much simpler method than using the long, rigorous way. So I'm going to stop this part 1 because I'm only allowed to record 15 minutes apiece on YouTube, so I'll see you back in a second on part 2.